Hello students, today we are going to start application of partial differential equation. Today we are going to derive two-dimensional wave equation with solution of wave equation. The same question can be asked in the exam in this way. Derive two-dimensional wave equation and its solution of wave equation. So please watch the video till the end and just practice this question. Definitely it is going to come in internal exam as well as I exam and your final exam, students. Either you are from BTU or any engineering colleges, application of partial differential equation is very important, and this is very applicable to all the fields of engineering. We'll just discussed few more things. This is a second video on application of partial differential equation. With the derivation, I'm going to do wave equation. So we'll just derive this equation. So whenever this question comes in the exam, please see that. You draw the diagram and then you explain in your own words. Within half an hour, you're going to get the knowledge of how to derive wave equation. Very simple, and very few steps are required to derive wave equation. For solution of wave equation, definitely some more steps is required. So this is a small idea about how we are going to derive. There will be one diagram, explain the diagram, and in the examination point of view, you are going to derive the wave equation using the partial differential equation. So please, yes students, please remember that when you are going to derive wave equation, you are going to come across partial differential equation. Please say that partial differential equation, we already have so many lectures on partial differential equations. Here we see some more video lectures in my YouTube channel. You can just go through my YouTube channel, just subscribe button is there, please subscribe, so that some more such videos I'm going to upload in my YouTube channel, Engineering Mathematics Made Easy for All. In this playlist you can come across, here we can see I uploaded already 6 videos partial differential equations. Some more videos I will upload definitely, and it will be helpful for your any type of examination. Even in the GATE exam, they are going to ask this question for 1 marks with different parameters. Yes friends, if you support and if you just subscribe, right, I will make more videos on partial differential equation. So whenever we start deriving wave equations, friends, please say that you be there with end of the video. I'm going to derive wave equation and its solution. Hardly it will take 15 to 20 minutes to derive, right? So just saying that partial differential equation you should know before watching this video. I've already derived wave equation. So here, just a minute. This is one-dimensional wave equation. Two-dimensional wave equation also you will get, but in this video I am going to do one-dimensional wave equation. If you want two-dimensional wave equation derivation, definitely I will derive, no problem. You have to just like and comment on the YouTube that please make a two-dimensional wave equation. Definitely I will make two-dimensional wave equation. This video is made only for the students, those who want to understand wave equation, friends. What I was saying is, before deriving wave equation, this is the second video of derivation. So in the first video already we have discussed one-dimensional heat equation. Yes friends, one-dimensional heat equation I have already told it is the heat is going to transfer from hot body to the cold body, where you can see as the length increases, temperature decreases in the conductor. Just go through the previous video, friends. You can see in the screen, it's clearly how the temperature goes on decreasing as the length increases. So this is a small graph we already seen, and in my last lecture, application of partial differential equation we have discussed, where we have come across one-dimensional heat equation. Now I'm going to derive wave equation. In the next video, I'm going to derive Laplace equation. So wave equation. Today's lecture will be on derivation of wave equation. The simplest situation to give rise to the one-dimensional wave equation is the motion of a stretched string, specifically the transverse vibration of a string such as the string of a musical instrument. So you have just seen the musical instruments. There we have just going to have the strings. You can see this wave equation. In this wave equation, you can just have drawn the x-axis and y-axis. How the wave is going to travel, you should know before starting of the class. You should remember that wave, how the wave is going to travel from one place to another. This is a very simple diagram I have drawn. Just look on the screen how the wave is going to travel from one end to the another end. So this is a simple diagram, direction of wave propagation. Mathematically we see there is amplitude, there is a trough and crest in this, and here we can see this is a wavelength, one wavelength, one thrust and one crest, trough and crest, one will make the wavelength. And you can see this is the compression and refraction, sorry. So you can see how there is a rarefaction when it is trough, and when it is crust, how it is compression takes place. So you can just see on the screen. So this is all the idea about how the wave propagation takes place, what is the wave diagram we have. And now we'll go for the derivation of this. Very important. Stay tuned in this video till the end of the lecture. We are going to derive wave equation and its solution. So please be watching the full video. So I'm going to derive now. In this channel, I'm going to give the link also. Your partial differential playlist is there. You will get it. You can solve many examples on partial differential equations. Yes, friends. So here we are going to derive the partial differential equation. Application of partial differential equation. In the last video, already we have discussed derivation of one-dimensional heat flow. Please watch that video, students. Then only you will understand how the one-dimensional wave equation I am going to derive. In the similar lines, the same derivations are there. So these are the two videos I have already made it. Just you have to watch it sometime and practice this example. Is it clear? So this is derivation of one-dimensional wave equation. Today we are going to derive one-dimensional wave equation. Before this lecture, see that you go and watch the heat equation flow. Okay, without wasting your time, we'll just go to the derivation, students. Yes, here we are going to derive. Very important. First, when they ask such type of questions, see that you first explain the diagram. First you draw the diagram, explain the diagram, then whatever you are going to get the proportionality that you are going to write, and then we are going to simplify. Now we are going to derive one-dimensional wave equation. We are going to start. Now, whenever we are going to derive wave equation, consider a homogeneous elastic string of length L. Yes, I just discussed that how the wave equation, there is a string which is going to stretch, and this is in that diagram I have discussed that how homogeneous elastic string of length L is there with uniform density rho stretched tightly between 2 points O and A, subjected to a constant tension T. So this is what we have to write in the exam. Now, let me just take this. Yes. A simple diagram you can draw here, students. Draw the x-axis. This is x-axis we are going to draw, and take the another axis I am going to take. So that will be y-axis. So this is x-axis I'm going to take, and this is u-axis I'm going to take. Because in the last video I have already discussed u is a function of x and t. So here we'll describe this, no problem. So this is a wave I have taken, one single wave I have taken. Suppose if you take any x-axis and y, here x-axis and u-axis if you take, right friends, you are going to take only the one wave. So this is a simple way I can say, this is a simple way I'm going to take. Here we can see in this, what is the function students here? It is u of x comma t. Please remember this students. So this is u is the displacement. I'm going to say this is the displacement at time t. At time t, u is the displacement. Then we see in this distance you are going to take this as u, and this distance will become x. Is it clear? At point, just say this point where the vibration takes place, this is because of the vibration. Is it clear? And this I will take at point A. This I will mention this point A, where this at point this position in your string or the wave is going to be equilibrium. So these all things you have to remember. Always students, it will start with the initially 0. So keeping this in your mind, I am going to draw mathematically how the diagram I am going to take. I am going to take only this part. So this is the wave I have taken here. In this I am going to take a point P at a position x comma u, and I will take second point, that is q, at x plus delta x and u plus delta y, u I am going to take. So at point P, the distance traveled on the x-axis is x, and at point Q, the distance traveled on x-axis is x plus delta x. This is a small change in the displacement. Okay. So this is all you should remember. Hardly it will take 2 minutes to dot this diagram. Is it clear? So what to say? Consider a homogeneous elastic string of length L with uniform density rho stretched tightly between two fixed point O and A, subjected to a constant tension T. That's it. Then take O as the origin. I have just discussed in the diagram. So u x comma y, rho u comma t. You can just say that this you can write in your own words. No need of writing as it is. This is for your understanding. I have written is the displacement of a string from its equilibrium position at point x at a time. Assume motion takes place in ux plane. So just we take this diagram. In the diagram it's clearly mentioned it is ux plane. Now we start deriving it one by one. Consider a motion of a small element. Consider a motion of a small element pq. So I'm just going to take pq of a string between px comma, yes, here I will take this as x comma u, and because u plane is there, so I will just take this as u plane. So in some of the books they have given y, but here in this case I am going to take u. So always remember, in partial differential equation two independent variables must be there. So here I have taken x and y. Okay. So let alpha and beta be the angle made by the tangent at P and Q respectively. By doing this process, we get the acceleration of the element is dou square u upon dou x square, vertical direction. So let us draw this alpha. So at point, I will just take the pen. Okay, at point P, there is an angle alpha. So I'll just draw this line and say this is the angle alpha. And at point Q, there is an angle, another angle from this line. That's I'm going to draw the tangent to this line T. and which is a tension on this string. This angle is going to become beta. So this distance is nothing but we'll take this as dou x. Is it clear, students? Any doubt, please comment. We'll discuss more things on this. So this is all about the diagram we are going to write. There are two forces acting on a string. Please remember there are two forces acting on a string. One taking away from the equilibrium position and another force is bringing string to the equilibrium position. So this is away from equilibrium position. So I say that this is our equilibrium position. Equilibrium position. And one is taking close to the equilibrium. So two forces are acting here. Two forces are acting. Is it clear, friends? So these all things you should remember. Now we are going to derive the equation. This all general things you should remember, how the string is going to take, how the wave equation is going to be drawn. Then we start our calculations. Yes sir, students, just be very important step. Therefore vertical component of the force acting on the element T is so large, weight is neglected with the angle sin alpha and sin beta. So here we just see Q minus P, or at point Q and at point P. So it is, we have just subtracted the 2 points. If you just look on the diagram, so at point Q we will get T sin beta and at point P minus T sin alpha. So that part we are going to calculate. When theta is the angle small, then sin theta is going to become tan theta. So the angle is very small. We just consider this theta, sin theta will become automatically tan theta. So therefore it means that sin alpha will be written as tan alpha and sin beta can be written as tan beta. So it is close to the sin and tan. Its angles are close, very the values are between these are very close. So now we'll derive this, friends. Now okay, just take the pen. Now here see, for your understanding you'll write what I am going to simplify from the diagram. Suppose this is at point P, this is change in the plane U and this is change in the plane x plus, and this is alpha is there, then what will be the value of tan alpha? Yes students, you please remember this will be opposite upon adjacent. So you please see here, you are going to get this as dou u upon dou x, dou u upon dou x. But when you take alpha, this is at point P I will get, so the distance will be x distance. So I will write here x. Similarly at point Q, if this is angle beta, then this is change in the u axis and this is change in the x axis, then what will be tan beta? Yes students, it is change dou u upon dou x, but here at point Q the displacement is x plus delta x. So these two values I am going to substitute. The same way we have already derived in the previous lecture while deriving the heat equation, the same way we are going to solve this derivation. Now I am going to substitute this equal to T, let's substitute this, friends, T dou u upon dou x, x plus delta x minus dou u upon dou x. I've just substituted this value from the diagram, which you can say from figure these values are calculated. Okay, now I want to simplify this. So t is common, I have taken t outside. Remember, t is common in this equation, so I have taken t outside and I substituted only tan alpha and tan beta in this equation. That's nothing I have done. Now when we consider always the mass of the element, let's see here, what is the mass of the element here, friends? When we consider mass of the element, in this case this mass is nothing but the whatever the density is there and change in the distance. So what is the mass of the element? Please remember this, friends. I'm going to say this mass is nothing but whatever the density of the element is there into whatever the change in the displacement, or you just say it as displacement. So please remember the mass, friends. Density we already defined it as rho, and displacement we already considered this as change in the displacement, that is delta x. Okay, next another one thing you have to remember here, friends, that is Newton's second law. Yes, I think everybody knows by Newton's second law. Everybody have come across. What is the force, friends? Please remember, force is nothing but force equal to mass into acceleration. Yes, friends. So mass, I am going to substitute this value. Acceleration you have come across. What is acceleration? It is change in the rate of change of velocity. Rate of change of velocity is nothing but rate of change of speed, which is nothing but the displacement. So therefore I'm going to take this m, we substitute from the above equation, that is rho into delta x. Is it clear? Into, now acceleration, please remember here, friends, rate of change of velocity. Rate of change of velocity is nothing but again rate of change of displacement or speed with respect to time. So therefore this will be dou square u upon dou t square. So just substitute this value in this equation, friends. Dou square u upon dou t square, which is equal to, so this is mass and this is acceleration, which is nothing but the force. So force we have already calculated, vertical force, students, vertical component of the force. Just now we have calculated, just substitute in that. This is going to be t into dou u upon dou x, x plus delta x minus dou u upon dou x at distance x. So this equation is very important equation, very important. Don't make mistake in this equation. So now we'll just simplify and we'll get the derivation. Yes, friends, what will be that? So here I can see delta x, I will bring it in the denominator, and rho I will bring it on the denominator. So these two values I am going to bring it here. So that will be dou square u upon dou t square is equal to t divided by rho. Just simplifying, yes, friends. So now this part you are going to get dou u upon dou x. Just mathematical calculations, just simplification I am going to do here, friends, this equation, and I am going to use some limit to get the better result. Yes, friends. So I have just simplified this equation. I brought this value in the right hand side. Now proceeding in this way, limit I am going to take, taking limit on both the sides, friends, as q changing to p. Yes, in the point q, when it comes to p, whatever the change in the displacement or distance will become 0. So this will be there on both the sides, So in left hand side you can here see here, students, there is no delta x, so there will be no change in this. So using first principle of derivative, What I will get here, students? Dou square u upon dou t square as it is, no change. T upon rho is constant. So what will be limit as delta tending to 0? What will be this equation? Dou u upon dou x, x plus delta x minus dou u upon dou x, x divided by delta x. What will be this equation, students? Can anybody tell me? Yes, please remember, very important, by using first principle of derivative. Yes, friends, by using first principle of derivative, limit as delta x tending to 0, dou u upon dou x, x plus delta x minus dou u upon dou x, x divided by delta x. This will give you students dou f upon dou x, but here f is nothing but here already dou u upon dou x. So here I say this is dou upon dou x f, but here f is the function. This is going to become f of x plus delta x minus f of x. So therefore I can write this as dou upon dou x, dou u upon dou x, which is nothing but dou square u upon dou x square. That's it, students. You have to remember only this part. If you don't remember, at least you can directly substitute this value. Therefore, so here I will get dou square u upon dou square u upon dou t square is equal to t upon alpha, t upon rho. I will put t upon rho. Some constant is there, so I will just mention this square. Say I am going to take this constant, so I will just take this as c square. Whatever limit is there, I am going to substitute this as dou square u upon dou x square. Is it clear? Therefore, this is our one dimensional wave equation. Is it clear, students? And this is hyperbolic equation also. It's also known as hyperbolic equation. If you compare the equation, it is hyperbolic equation. This is how we have to derive the one dimensional equation. Very important, very simple it is, students. Immediately go to the solutions of wave equation. Definitely in the exam they will give wave equation, derive wave equation and its solution. Solution is very easy. Don't worry, not so difficult. After deriving wave equation, if you understand how to do wave equation, solution is very easy, students. So again, please remember, previous lecture already solved solution of heat equation. Same way we are going to take the solution of wave equation. If you join the video of heat flow, solution of heat flow, the same way we are going to derive wave equation. Okay, so let us derive the wave equation quickly, students. Without wasting your time, take by the method. Which method we are going to use, students? Can anybody tell me? Yes. If you just see the previous video, you can just say that it is by separation of variables. Yes, friends, we are going to separate these variables. Right hand side x and left hand side we are going to take t. When we are separating this, friends, please remember the equation of wave equation. Which equation we are going to separate this? Yes, it is dou square u upon whatever the above equation just now we have derived. The same equation just take down once again dou x square. So I will keep this equation number 1. Now I say that can anybody tell me what is the solution of this? Yes, in my last video I have just told you this u, I am going to take this as solution x into t. X is a variable of x and t is the variable of t. So x is nothing but the variable of x, where we can say where x is a function of x and t of t is a function of t. So these two variables I am going to take as friends. Now I will simplify one by one in the equation 1. So dou square u upon dou t square, how we are going to write? So just differentiate this equation 2 times with respect to x and differentiate this equation 2 times with respect to t. So just remember this ones, differentiate, I will take this equation suppose star, differentiate equation star with respect to x twice and differentiate equation star with respect to t twice, means double differentiation I am going to write here friends. You are already perfect with double differentiation, so directly write this as dou square u upon dou x square is equal to t is constant, so I will write t as it is, no change. When you are differentiating with respect to x, so it is going to become d square x upon dx square, because only one variable is there. If there is one variable, you can use partial differentiation or ordinary differential. There is no change in this differentiation. Is it clear? And why I have written d is very very important. You understand this, okay? And dou u upon dou t square dou square u upon dou t square is equal to, here x is constant, so I will take x as it is, and I will take dt square d square t upon dt square. So why I have taken here d here friends? Because only one variable is there. Whenever one variable there, partial differential equation or ordinary differential equation, the answer will be same. Therefore I have written in terms of ordinary differential equation. Okay, now I am going to substitute this in this equation star. Okay, so when I substitute this both the equation in star, so substituting in equation from star, I have clarified this ones, separate x one side and separate t one side. So this will be t, I will bring it on t, and c I will bring it on this side, x I will bring it on this side. So we are going to separate this x and t variable. So this will be 1 divided by c square t d square t upon dt square is equal to 1 upon x d square x upon dx square. So this is the solution. So when I get this solution, this I am going to take this as some value k. So I am going to say this, or just consider this as k. Is it clear? Okay students, now I am going to simplify. LHS must be only t variable and RHS must be, this part must be only x variable. That is the separable variable method we have done. Now we have completed the separable variable method. You want to solve some more examples on separable variable method, you can go to the playlist and you can see in that I have solved many examples on separable variable methods. So this way we find the separable variable method. Thus now I am going to equate this to k. So what will be the values friends? Yes, I am going to take 1 upon x d square x upon dx square is equal to k, this part, and I have to solve 1 divided by c square t d square t upon dt square is equal to k. So either this is the solution and this is the solution. When you get this both the solutions with respect to x and t, that will be our final solution. Okay, now I will just simplify. So I will simplify simultaneously both this equation. So this is dou square x upon d square x upon dx square is equal to x into t, and d square t upon dt square is equal to c square k, and I will take t. I will take this xt on this side and c square kt on this side. So I will get the equation in this way, students. It is dou square x upon d square x upon dx square, sorry, minus kx is equal to 0. Similarly, d square t upon dt square minus c square kt is equal to 0. We always equate it to 0 so that simplification will become very easy, students. Okay, now this is what we get the equation. Whatever the solution of these two equations are the final answer. But please see here, there are again three cases. K, we don't know, it is positive, the equation will change. If it is negative, both the equation is going to change. And if K is 0, sometimes when the specific temperature or the specific heat what we have taken it is 0, that time the wave, if there is no change in the wave, then it will become 0. So when the wave is according to the direction, it will be positive. If this wave is opposite to the direction, the K is negative, and if there is no wave in the string, then it will be 0. So these three cases arise in this equation. So I will take the case 1. Case 1, K is positive. Okay, when K is positive, students, I will consider this K is some lambda square. So which lambda is real. Okay, lambda is real. Okay, now I'll just simplify this, students, very easily. Already in such examples we have already done. So here whatever differentiation d upon dx is there, I'm going to take this as a d, and please remember this, students, d square upon dx square is there, it is going to become d square. That implies, if you remember this equation, this is going to become d square x minus kx is equal to 0, or I'll take x common, so this is d square minus k x is going to become 0, and here this is going to become d square t minus c square kt is equal to 0. In this two, t is common, so I'll take d square minus c square k t is equal to 0. So we get this equation. So immediately after getting this equation, you are going to write this equation in terms of auxiliary equation. What is auxiliary equation, students? Just you have to substitute d square is equal to m square. That implies, what will be the auxiliary equation of this equation, students? It is m square minus k is equal to 0. This will be equated to 0 always, and this is m square minus c square k is equal to 0. We get this two equations. Now okay, I have taken here lambda, right? So this k is going to become lambda square. Yes, here I have taken k is some lambda. So please change here, k is equal to lambda square, you have to substitute only lambda square in this equation. Okay, so you can just change this, wherever k you have taken, just make this lambda. Lambda is real, so that is why we have taken this as lambda. So please make the changes here. This will be lambda square. Okay, I'll just repeat this. K is positive and k is equal to lambda square, where k is some real value I'm going to take. So just substitute in the previous equation. D square x minus lambda square x is equal to 0. D square minus lambda square remains, x is common, which is equating to 0. In this case it is d square t minus c square lambda square t is equal to 0, and d square minus c square lambda square I have taken outside, t is common, which is equal to 0. Auxiliary equation, this equation you will get the answer when m square minus lambda square is equal to 0, and you will get the solution by using auxiliary equation. This is m square minus c square lambda square is equal to 0. So this is a simple idea. Now we will simplify this, friends. M is equal to plus or minus, we get lambda, same whereas here m is equal to plus or minus, we get some c lambda. So there are two solutions in this, m1 and m2. m1 is plus and m2 is equal to minus lambda. Here again m is equal to plus c lambda and m1 I will take, and m2 is equal to minus c lambda. So there are two values. So the roots. Okay. Then what will be the solution? Directly we take the solution here, friends. What will be the solution? We say that x is equal to c1 e raised to m1x. So lambda x plus c2 e raised to minus m2x. So here minus lambda x we get. This is the solution. Similarly, with respect to t, what you will get here, friends? It is c3 e raised to c lambda t plus c4 e raised to minus c lambda t. So these two equations we will get. Now suppose this k is negative, the wave is in the opposite direction, that time we get the case 2. What will be case 2? K is negative, and when k is negative, please remember we take k is equal to sum minus lambda. So this I am going to consider, and where lambda is real. Okay, let lambda be the real value, then only we can find the solution. Okay, again we are going to repeat the same way, only here k is equal to minus. So we are going to substitute in the solution of wave equation. So we are deriving the wave equation, just substitute the values, friends. Directly I will take, now you have understood what is auxiliary equation. This is going to become m square, minus into minus is going to become plus, lambda square is equal to 0. So m will be plus or minus, it is I lambda, because minus will get this side, and you can see root of minus 1 will be always I, and square root of lambda square will be lambda. And similarly auxiliary equation of this part, what will be this equation? Auxiliary equation, friends, auxiliary equations will be lambda square plus m square plus lambda square c square is equal to 0, or m is equal to plus or minus I lambda c. Again here please remember here, friends, this plus will become, this side will become minus 1, therefore I will be equal to minus 1, I square will be, sorry, I is equal to square root of minus 1, and square root of lambda square c square can be written as lambda c. So these two equations I am going to substitute, I will get here m. So this is compared with the imaginary root. We can see the roots are here, both the roots are imaginary. Please remember here, students, the roots are imaginary. Here also roots are imaginary, and the roots are imaginary, students. Compare with the imaginary root. So in this you can see the equations we are going to compare with the solution, where it is given alpha plus or minus just a minute. Alpha plus or minus I beta. I am going to substitute. What is the solution of this imaginary root, students? Yes, the solution here is, remember the solution, students. Solution will be x equal to c phi cos lambda x plus c6 sin lambda x. Is it clear? And similarly on this side it will be t is equal to c7 cos lambda t ct. Yes, c is there, so c I will take here, and plus c8 sin lambda c t. This is what we get the solutions. So these are the solutions when k is negative. And last and final part, students, we finish the solution now. The last case, that is case number 3, when k is 0. When k is 0, please remember k, I am going to take this as 0 value. Therefore directly you will get the solution. There is no solution directly. M square will become 0, and this will be m, having m1 is 0 and m2 is equal to 0. Similarly on this side also, m square will become 0, m1 0 and m2 is 0. So there is two values. M square means m into m. So there will be two values 0. This side two values will be 0. Therefore the solution will be x is equal to a, or just take C8 I have taken. So here also I'll just make this as C9 x plus C10, and in this case the solution will be t is equal to C11t plus C12. These are the solution. Yes friends, that's it. The derivation is got over. Therefore we substitute this x and t in our initial conditions. Therefore what is the possibilities, students? Thus the possible solution of wave equation. That's it, students. Like derivation is over. Equation R. So what are the solutions we have taken? First one, already have to substitute in this equation u is equal to x into t. And the beginning only we have started with the initial conditions. So this is u is equal to x into t. That's it. So I have taken u is equal to, please remember this, c1 e raised to lambda x plus c2 e raised to minus lambda x into c3 e raised to lambda ct plus c4 e raised to minus lambda ct. This is the solution. Second one, please remember u is equal to, substitute the values, c5 cos lambda x plus c6 sin lambda x into c7. This is just a constant, students. Please remember lambda ct, c1 c2 are just constant. You can take any constants as you like. Lambda ct, this is there. And the last solution we have calculated, that is u is equal to c9 x plus c10 and into c11t plus c12. These are the solutions. Thank you so much, friends. Thank you for watching, and please subscribe. It will motivate me to do some more videos on this. Yes friends, thank you so much. We will continue in the next class. Next will be the Laplace equation. Please see that